Hey physics friends, Mr. Collier here, and today is our third and final video for Chapter 6. We're going to look at objects colliding today. We're going to look at collisions. There's two types that we're going to talk about, elastic and inelastic. We're going to define them and talk about the math that goes along with them. First, some very important concepts. First is conservation of momentum. This idea is that if two objects interact, whether they collide or they push off of each other, then the total momentum of the system is conserved. It's a constant value. So this means your mv before is equal to your mv after, right? Now, maybe it's multiple objects, right? Maybe you've got an M1v1 and an M2v2, right? Like two different objects. Whatever their momentum before, right, still needs to sum up to their momentum after. M1v1 plus M2v2 afterwards. That's another way to write it. Momentum is conserved, it's constant before and after the objects interact. This is also related to the conservation of energy. Energy is neither created nor destroyed. However, just because energy is neither created or destroyed doesn't mean it can't be turned into less useful types of energy. And so collisions are going to be classified based on what happens to their kinetic energy. Some collisions will lose kinetic energy and some will not. The energy is not destroyed, but it will just be converted to unuseful forms. So the first type of collision that we're going to talk about is what's called an elastic collision. These are considered ideal collisions where zero kinetic energy is converted into thermal energy. In other words, 100% of that elastic kinetic energy is conserved. So for example, we consider springs and magnets and billiard balls to be approximately elastic collisions, but really they also lose a little bit of energy. But in elastic collisions, we see all of the energy in coming out as kinetic energy. Now the true elastic collisions exist at the atomic level, and you might remember that from a chemistry class when you talked about how gases have these truly elastic collisions. So let's take a look. This is called a Newton's cradle, where you've got a ball clinking against other balls. And if one ball goes in, one ball goes out, right? The momentum is equal to mass times velocity. The kinetic energy is 1/2 mv squared, and so whatever goes in comes out. And so if you double the mass going in by sending two balls of the Newton's cradle in, then two balls are going to come out. That's, again, an elastic collision. The things bounce off of each other, and the momentum that comes in is the momentum that comes out, but also the kinetic energy that comes in is the kinetic energy that goes out. So this is not going to happen in this last picture. You're not going to have one ball come in and two balls bounce out. So you can play around with a Newton's cradle, have one of those in class. So now let's look at this from a mathematical perspective. Really what we're saying is that the initial and final momentum are equal to each other, and the kinetic energy before and after is also equal to each other. So say you've got multiple objects, right? You've got your m1 and initial velocity, your second mass and its initial velocity. They are going to be equal to the mass times the new velocities for the objects added together. In other words, the momentum before equals the momentum after, and the kinetic energy before, when you sum those up, is equal to the kinetic energy after. So you'll use these equations as you go into some of your homework problems. Now the other type of collision is considered an inelastic collision. These are real-world collisions. Some of the kinetic energy is converted into thermal energy, heat, maybe sound, and so not all of the energy that goes in comes out as kinetic energy. Now, momentum is still conserved. So there is a special case called a perfectly inelastic collision, or completely inelastic, where two objects that run into each other actually stick together and become one new mass. So mathematically, the momentum will be conserved, but the kinetic energy will not. Let's take a look at this. So say that you've got the initial and final conditions for this, right? In this case, they each have their own mass and their own velocity to begin with, but at the end they become a single mass with a single velocity. Again, that's that perfectly inelastic collision that we're seeing. So let's say that this first car has a mass of 10, the second car also has a mass of 10. So the two cars have equal mass, both 10 kilograms. Car 1's going 10 meters per second, car 2's going 2 meters per second. What happens after their collision? So if we hash that out, we know that momentum is conserved. So the sum of the momentum will equal the new total mass times the new velocity. So 10 kilograms times 10 meters per second plus 10 kilograms times 2 meters per second equals 20 kilograms, their combined mass times the final velocity. So you simply multiply, add, and then solve, and you'll find that the final velocity is 6 meters per second. And that's, again, just because of the conservation of momentum. The momentum they have individually is equal to the momentum they have after the collision when they're combined. Now, we can actually show that the kinetic energy is not conserved. So now we can calculate the kinetic energy before the collision. 1/2 mass times velocity plus 1/2 mass times velocity. We can figure out that the sum of the momentum of each of these cars is 520 joules of kinetic energy. Then after the collision, they've got 20 kilograms of mass now, but notice their speed is that new speed that we just calculated, right? So we've got 360 joules of kinetic energy. So some of that energy was lost, specifically 160 joules. That must have been transferred somewhere else, right? So maybe it was friction, heat, sound, the deformation of the two cars as they collided, etc. So in summary, momentum is always conserved. Total mechanical energy is also conserved during a collision. However, kinetic energy might not be, right? So you're going to be looking at these in your homework. The equations you want to remember is that the initial momentum is equal to the final momentum. In other words, the sum of the momentum of the objects before is equal to the sum of the momentum of the objects afterward. And so you want to think like, is the object moving? If it's not moving, zero velocity means zero momentum. And then you're going to see some different things. You're going to see like a gun recoiling, right? So at the beginning, the total momentum is zero because the gun's not moving, the bullet's not moving. And so afterward, they're going to have opposite directions and they should add up to zero. You're going to see different types of collisions, right? Elastic, things bouncing off of each other. Billiards is a common example in that type of problem. And you're going to see some inelastic collisions, some perfectly inelastic where things collide. I might do a whole separate video on some sample problems as some of these conservation of momentum calculations can get fairly complicated. But that's what you need to tackle conservation of momentum. Good luck.